Yeah, good evening. Hello. Hello, good evening. Sound sound please. Yeah, welcome to today's live session. This is the first time that I am doing the live session. So today, in this live session, what we discuss is we'll start with basics required to understand probability and statistics to a maximum extent later. So that is, we'll go through the basics like principles of counting, basics of set theory, and how to define probability. So slowly we'll get into the advanced topics in the consequent sessions. So to begin with, this is the simple rule, the basic principle of counting, which we are going to use regularly, and we are already familiar with respect to this rule. So this is suppose any event A happens or is happening in M ways or M types, and another event B happens in any one of n ways. Right? So two events, for example, here to begin with, we consider two events. That is, A happens in m ways and B another event happens in n ways. Then if we want to find the total number of possible ways where both A and B can occur or happen, so that is nothing but m into n ways. Right? So this is the regular kind of formula or approach we use. Simple example, suppose if A to B, if you take any simple example, A to B can be traveled or we can travel from A to B in two ways, suppose. And B to C, there are three ways that we can travel. Now, how many ways that we can travel from A to C if we want to answer, right? Then simply we know this basic mathematics says it is 2 into 3, that is 6 ways, right? Right. So this is what we call as the basic principle of counting, right? So here A happens in m ways and B happens in n ways. Then the events A and B happens in m into n ways. Right? So this is the basic principle which we are going to use in regular intervals. Now, for example, if you take here, suppose if you take one is tossing of a coin, right? And another is throwing a die. Right? So two we are doing. Right? So one is tossing a coin, other one is throwing a die. So we know if we take tossing of a coin, so that can be done in two ways. Our possible outcomes are two. And in the second case, even B, throwing a die, there are 6 possible ways, right? Or 6 outcomes that we can have. That is, 6 outcomes are nothing but 0, 1, 1, 2, 3, 4, 5, 6. And if we say what are total possible outcomes combining these two events together, if we say, that is nothing but 2 into 6, which is 12. Right? So this is, so knowingly, unknowingly, without uttering this, so we use this frequently in this course. Right? So that is called as the basic principle of counting. Right? So not only two events, now this same phenomena can be extended where multiple events or many events involves. Right? It need not be only two events. Right? So it can be extended to many events. Right? So that is as shown here. So that is the extension of A1, A2, A3 and so on, AN or AK can occur in N1, N2, N3 and so on NK ways. So then the total number of ways that all the events can occur together is nothing but the product of all the possibilities or possible ways. So therefore N1 into N2 into N3 into and so on NK. Right? So this is the generalization of the basic principle of counting. Right? So now the same in another form. Another form is here in the earlier two cases where we discussed happening of both together, right? Either A event as well as B event happening together. So there M into N or N1 into N2 into N3 and so on comes into picture. So here same way, but here instead of both the events, if how many ways either A event or event B occurs, right? So I think it's very clear. The previous case, what we discussed is happening of both the events or occurrence of both the events, right? Where m into n comes into picture. Whereas here either happening of event A or happening of event B. So this happens in m plus 1, m plus n phase. Right? Okay. So in the same fashion, this also we can generalize, which can accommodate as many events as possible. Is not restricted only to 2 events or 3 events. Like the previous generalization of counting principle, this also can be generalized where n1 plus n2 plus n3 plus so on ways we can. So I think so here we need to understand there in the previous principle of counting it is happening of both, whereas here happening of either event A or event B. Okay. So next we'll get into the basics required for the probability. So basic required for the probability whenever we start probability. So we define some terms which are essential for us to understand to get into the probability concept. So the first one is random experiment. The first term to begin with is random experiment. So what is this random experiment? And we are familiar with respect to the term experiment. Experiment is something which we do in laboratories in physics lab or chemistry lab. Whatever we do, we call them as experiments, right? Here, so this term is random experiment. So what is the difference between that experiment and this random experiment? The experiment which we do in laboratories, that is where with the all the apparatus, where the outcome is known, right? So here in the random experiment, where result is not unique, and we know what are all possible outcomes related to experiment. Simple example, if we do an experiment in physics laboratory related to finding the gravitational force, so the result is unique, right? So where we are going to validate whether G equal to 9.8, so what is the G at a given place, right? But in case of random experiment, what happens is the result is not unique, but it can be any one of the possible outcomes, right? So that is what we call as random experiment, right? So an experiment where the outcome is not unique and it is any one of the possible outcomes, right? So the simple examples, now if we take tossing of a coin, if we toss a coin, so either we may get head or tail, right? We may get a head or tail, that is any one of these two is the outcome of this experiment, therefore this is called as random experiment. Similarly, throwing a die, right? So, throwing a die, so we know, right? So see, when you throw a die, it can be any number, right? It can be any number from 1 2 3 4 5 6, right? It can be any number. We are not saying that we are going to get either 1 only, 2 only, 3 only, right? It can be any one of all possible outcomes, right? Therefore these are an examples, or these are called as random experiments, right? So uh, so now onwards, wherever we use the term experiment, means it is nothing but random experiment. It's not necessary that we are going to use the term random experiment always. Here experiment means obviously it is a random experiment in statistics. So next is sample space. So what is this sample space? Right? So whenever we take a random experiment, right? So as discussed just now, so all possible outcomes, right? any one of the possible outcomes, right? Any one of the possible outcomes. Suppose if we take a random experiment, if you list out all possible outcomes, right, and if you put it in the set form, then it is called as the sample space, right? So for example, the regular examples which we have been using, so if we take tossing of a coin is an experiment, right? Tossing of a coin is an experiment. That is nothing but, as discussed, it is a random experiment. So we know when we toss a coin, either we may get head or we may get a tail. Right? So these two are the possible outcomes related to the experiment, that is tossing of a coin, right? Okay. So if we put this in the set form, and generally we denote it by S. So this is called as the sample space. Okay. So like this, suppose if we take another example, that is throwing a die, right? So we know if we throw a dice, so then all the we know the possible outcomes, right? So either we may get 1, 2, 3, 4, 5, 6. Right? So if we take the set consisting of all the possible outcomes from 1, 2, 3, so on up to 6, right? So this is called a sample space. Okay. So that means, so sample space is nothing but the set consisting of all possible outcomes related to sample space. So this, like this we can continue. Suppose for example, here if a coin is tossed 3 times, right? So 3 times, so every time it is having 2 possible outcomes, right? So 3 times we are doing 2 into, right? So 2 into 2 into 2, that is 8, right? So all 8 possible combinations with respect to head and tail, if we list out, we'll get all these all heads, 2 heads and tail, HTH, like this, right? So the set consisting of all these 8 possible outcomes, if you take, that is called as the sample space. Okay. So that is random experiment and sample space. Okay. So next, trial or event, right? So very simple. Now by this time we understand tossing of a coin is a random experiment, right? Tossing of a coin is a random experiment or experiment, right? Right? So it is nothing but trial, what we can call as. So if we toss a coin, as discussed, we may get either a head or a tail, right? So getting a head is called as an event. Similarly, getting a tail is called as an event. That means, so how to what is the definition of event? So event is nothing but a subset of the sample space, right? So event is nothing but the subset of the sample space. Suppose if we take an example like throwing a die, if we consider the example, right? Throwing a die, if we consider as an experiment, and we know the sample space contains the numbers 1, 2, 3, 4, 5, 6. Then can we try to define some events on this sample space? Yes, right. It may be getting a even number, getting an odd number, getting a number less than or equal to 2, getting a number less than or equal to 3, like, right? So like this, on a given sample space, we can have many subsets, right? That means we can have many events defined on the sample space. Right. So next term is exhaustive events or exhaustive cases. So exhaustive events means the total number of possible outcomes related to random experiment. All that means all possible outcomes, right? All possible outcomes are called as the exhaustive events or exhaustive cases. For example, here we take tossing of a coin, right? Particularly if we take the tossing of a single coin, if we take, we know we'll get either head or tail. Right? So then we say these are the exhaustive cases. So that means it now nothing but here in other way what we can do is if we take all these events here H union T, right? So then we have to get yes. Right? So whatever all possible events that we are defining on the sample space, if you take union of all these possible events, then we need to get yes. So then we say all these events are exhaustive events or exhaustive cases. So clear, right? So these are the definitions which we require and we are going to use regularly. Next, equally likely events. Right? So equally likely means, so it is very important, particularly in statistics, whenever we take an event, right? So whenever we do an experiment, then it should not have any bias, right? It should not have any biasedness, right? It should be unbiased, right? Right? So unbiasedness, if you take, then it is nothing but so equally like that means all are having equal chance of happening. Right? If you see the definition here, events are said to be equally likely if none of them is expected to occur in preference to others. Right? Suppose if you take a tossing of a coin, we know head and tail, right? When we do this experiment, then there is no preference, right? So head is having the first preference, tail is having second preference, like this, right? So there is nothing like preferences, right? So therefore, these are called as equally likely events. Right? So when in tossing of a coin, so all are equally likely events. That means the probability of, later I think we use this term, probability of getting a head, probability of getting a tail, all are equal, all are the same. Then the coin is said to be unbiased coin. This is important term for us. Unbiasedness is one of the important terms. So next important term and sometimes confusing term also, mutually exclusive events. Right? So when two events A and B are said to be mutually exclusive. Right? When two events A and B are said to be mutually exclusive. Right? So if happening of A, right, happening of A prevents the happening of B, right? Happening of A prevents the happening of B, right? Is not preventing, actually not prevents the happening of B, then the two events are said to be mutually exclusive, right? So for example, particularly tossing of a coin, if you take, getting a head, getting a tail are said to be mutually exclusive. Why they are called as mutually exclusive? Right? So because if head happens or head comes, it is not if head comes, that means we are not going to get tail. That means happening of B is stopped by or prevented by happening of A. So therefore these two events are called as mutually exclusive events. So very simple for us. So how to identify? So no logic is required here. If A intersection B equal to 5, if A intersection B equal to 5, right, equal to 5, then the events are called as mutually exclusive events. Right? If A intersection B equal to 5, that means if we take now, that's what we discussed. If we take the Venn diagrams, right? So we know this is A, right? This is B, sorry. sorry, this is, if you take A, if you take B, right, this 0, right? We know this is called as A union B, right? And this part is called as A intersection B, right? Right. Right. So this complete part is called as A union B, and this part is called as A intersection B, right? Right. Suppose if this A intersection B is not there, if this A intersection B is not there, right? So that means A intersection B equal to 5. That means you will have these two which are separated, so without any common part, right? So this is event A, this is event B, right? Right? So then the events are called as mutually exclusive events. Very simple. If any confusion is there with respect to definition, very simple. If A intersection B equal to 5, then the events A and B are called as mutually exclusive events. Next, independent events and dependent events. So here it's a very the name itself defines the events. So when two events are said to be independent events, right? The outcome or happening of one event is not depending on the outcome of the other, right? So if you see here, if happening of any one of them is not affected by another event, right, that means there is no dependency between the two events, right? So then the events are called as independent events, right? So now we can take example, like suppose two students A and B are there. Two students A and B are there. So they are in the class. Suppose there is only one rank, one first rank. So first rank will be awarded by the university for only one student. Right? Now we'll take two events. One is, the first event is A getting the first rank and B getting the first rank. Right? Now the question here is whether these two are independent events or not. Right? Right? So A getting the first rank, B getting the first rank, that means gold medal here. A getting the gold medal, B getting the gold medal. Whether these two events are independent or not. Okay. If here I think if you think if A gets gold medal, then B cannot, right? Right? So B getting the gold medal depends on A also, right? Right? So therefore they are dependent events, right? Dependent events, right? So if B gets, that doesn't mean he is stopping A getting the gold medal, right? That means they are dependent events, right? So another example, if you take A passing an examination and B passing the examination, right? So both are appearing for an examination, right? So a university examination, so where marks will be awarded. Now A passing the examination, B passing the examination, these are two events. So now whether these two are independent events or dependent events, right? Right? So passing the exam, right? So here independent events, right? So if A passes, it doesn't mean that B has to fail, right? So A can pass the exam, B can also pass the exam. That is, there is no dependency between both. Within brackets, if they copy, so that the situation won't come into picture, right? That is an assumption, right? So A passing the exam and B passing the exam are independent events, right? So clear, right? So how to identify? So this actually, when you take two events or three events and we try to understand the logic behind this, then we can come out with a conclusion and say whether the events are independent events or not. But how to identify? Is there any rule or any formula which helps us to understand whether two events are independent or not? Okay. Yes, there is a formula, we'll see. Okay. So this is the difference here. So what is the difference between mutually exclusive events and independent events? Okay. So what is the difference here? So very clear, it as discussed. So A intersection B equal to as shown here. So when A, B are mutually exclusive, then we'll have a diagram like this, right? Where probability of A union B equal to 0. Sorry, is it probability of A intersection B equal to 0? This is intersection. Right? So if A, B are independent events, if A and B are two independent events, then P of A intersection B equal to P of A into P of B. Okay. So vice versa also. Vice versa in the sense, for any two events A and B, if P of A intersection B equal to P of A into P of B, then the events are called as independent events. So this is a general question. In most of the interviews, the interviewer will ask to test the basic understanding of probability, right? Whether both are the same. So what is the difference between the two terms? Now I think it is very clear here. P of A intersection B equal to P of A into P of B is not 0, whereas here P of A intersection B equal to 0. So we have to be very clear with respect to these two terms. What is the rule here? What is the rule here? And if possible, with one or two examples which differentiate between mutually exclusive events and independent events. Okay. Now, so we'll go the actual definition of probability. Right? So, various forms of definition, various types of defining the probabilities are there. So here the most frequently used definition, that is classical or general definition of probability, is the same like what we have been discussing. Suppose take an experiment, random experiment, and we'll have the sample space, right? And assume that the sample space is having n entries. Right? Suppose consider any random experiment and immediately we'll have its corresponding sample space, yes, and assume that the sample space contains n elements. Now we define an event A on this sample space. Right? And out of n, m are in favor of this event. So out of total n in the sample space, m are in favor of the event which we define. Right? So then the probability of the event is defined as P of A equal to m by n. Right? So here n is total number of cases in the sample space, and numerator is the cases which are in favor of the event which we define. Right? So this is the basic definition of the probability. Right? Okay. Now if we want, we can take an example. Now tossing of a coin is the experiment, and we know the sample space, that is sample space contains head as well as tail, right? Okay. And now define an event, any event A. Suppose A is event of getting a head. Now we want to find probability of A. Right? Okay. So now how many cases are there in the sample space? How many entries are there in the sample space? Or what is n value? N value is 2, right? 2. Right? Now A is an event related to head. So out of these two, only this one is in favor of the event, right? So therefore it is 1 by 2. Right? P of A equal to 1 by 2. So this is the basic definition of probability. Okay. So the entire discussion which we are going to have depends on this basic understanding related to probability. So now one more definition, that is complementary event. Right? So that means negation of it, right? So if A is an event and not happening of A, right? Suppose if A is tossing of a coin, A is getting a head, then its complement is not getting a head, right? Suppose the event is passing the examination, complement is not passing the examination, right? That is, so complementary is nothing but not happening or non-occurrence of the event. Right? So where it is denoted by either A, C or A bar or A complement. Okay, how to define this? How to define this? Now from the earlier discussion what we had, we understand that probability of an event A equal to M by N, right? Okay. Now we want to find probability of complement of A, that is P of A bar. Okay. So that means here A is one event, A complement is another event defined on the sample space. Right? So now if we use the same definition, so how many total entries are there in the sample space? N, right? So total entries in the sample space are N, right? Now out of N, M are in favor and rest are against, right? That means not in favor of this event. So therefore this is N minus M. That means N minus M is in favor of not happening. Right? Suppose it is a 90 by 100 is a probability for passing the examination. Not passing the event if you take, not passing the examination if you take, it is 10%, right? That is 10 by 100, right? Because it is 100 minus 90 by 100. In the same sense here it is N minus M by. Right? Now we can write this as if N by N is 1 minus M by N. And if you observe the basic definition, this is nothing but P of A. Right? Okay. So that means P of A complement is nothing but 1 minus P of A. So that means P of event A plus P of its complement, summing together it is 1. That is total probability is 1. So this in some of the examinations, this can be asked, right? So prove that P of A plus P of A complement equal to 1. Right? So we can prove it by taking the basic definition P of A and P of A complement. From that also we can prove. Right? Or one in another way also we can prove this. How we can prove this is just to have another look. Suppose S is the sample space. If we take the Venn diagram and A is an event, right? S is the sample space. A is an event defined on the sample space. Right? Now from this we know A is this part, right? And A complement is rest of the right. A is this and A complement is outside. And if you take the union of A and A complement, A union A complement is nothing but the sample space, right? A union A complement is the sample space. Now here these two are mutually exclusive, right? A and A complement both are not having any common portion, right? Mutually exclusive, right? So therefore we can write this as P of A plus P of A complement. Right? And we know probability of sample space equal to 1. Right? Therefore we can write this as P of A plus P of A complement equal to 1. So this is the other way, by using this way we can prove this relation, that is P of A plus P of A complement equal to 1. Right? And one more important relation is this which we are going to use regularly when we try to solve numericals. That is P of A union B equal to P of A plus P of B minus P of A intersection B. So this is actually called as the principle of inclusion and exclusion. Principle of inclusion and exclusion. That is P of A union B equal to P of A plus P of B minus P of A intersection. So when we take examples, when we try to solve the problems, A union B is nothing but happening of either A or B or both, right? That is happening of at least one of these two events. This defines probability of happening at least one of the events, right? P of A. And P of A intersection B is nothing but probability of happening of both the events. So this is very useful relation or expression which helps us in solving many of the problems, right? And some observations, some definitions based on the definition of probability. There are some conclusions we can draw based on this understanding. Okay. So as per the previous discussion, P of A equal to N by M is the basic definition of probability. So here we know this is M is the total number of entries or cases in the sample space. And this is the number of favorable cases related to the event A. So therefore the probability of A. Here what are the two extreme cases? What are the two extreme cases? Right? So extreme in the sense, who is the luckiest one if all are in favor of, right? All the entries in S are in favor of. That is the most luckiest happening, right? That means all the elements in S are in favor of A. Then what happens? M by M, right? Then the probability is 1. So most luckiest case it is. So the probability of that event is 1 in such cases. That is going to happen perfectly, right? Therefore, that event is called as a certain event. Right? So what is the most worst scenario or situation here? Most worst scenario. Out of M, all are against this event. None of the entries in the sample space are in favor of this. Right? That may happen, right? So in your team, so no one is in favor of you when they are giving feedback, right? So in such cases, no one is favor, therefore 0 by M, right? So that means probability of happening of this event is not, therefore this event is called as impossible event. Right? So certain event as well as impossible event. But in true sense, if in such cases we don't require any probability concepts, right? If it is a certain, we don't require any probability. If it is an impossible event, we don't require probability concepts to understand. Right? Okay. Now, what are the difficulties here in this definition is, if the number of outcomes of the random experiment is infinite or unknown. Right? So here the problem with this is, if this n is not known, that is one case, and second case is, suppose this is not finite, the sample space is not finite, then it is a problem. You can ask, maybe you will have a doubt like, is there any example which says this definition may fail? Yes, there is an example. Suppose A is an event of selecting a star which is in color red from the sky. Right? A is an event of selecting a star which is in red color from the sky. Right? So here, we don't know the AM right, because S is an infinite set. Right? S is an infinite set. Probably we may have the value for n. Probably we may get the value for n, but S is infinite. So in such cases, this definition fails. Right? So that is the limitation for this. Okay. And one more point which we use regularly is, instead of giving probabilities, they use a term odds in favor of the event A is P is to Q. Then it is nothing but 2 is to 3 means the total 5, out of which 2 in favor of P and Q is against. Right? So in such cases, if they use this term odds in favor of, then it means P of A is P by the total, that is P plus Q. And P of A complement is, right, Q by P plus Q. And if you sum these two, P of A plus P of A complement, that is nothing but P plus Q by P plus Q, that is 1, right? Which is the one which we discussed earlier. Right? Okay. So now this generally in theoretical way of doing things will, like what we discussed earlier, right? There is a limitation for the regular definition of probability, right? Then, so we had another definition for probability, that is empirical or statistical way of defining probability. Right? So that is where, so we define it as probability of an event E, which is limit n tends to infinity m by n. So where n is infinity, like in what we discussed right earlier example, if the sample space is infinite set. Right? So to overcome this, so this is the definition which we call as empirical or statistical definition. Right? Limit n tends to infinity m by n. So another here three maybe in exam with respect to exam, so we need to have this. So three ways of defining probabilities. One is the earlier P of A equal to n by m, that is one way, and second one is the statistical definition of probability, that is limit n tends to infinity n by m. Third one is axiomatic definition. So it is axiomatic definition, or we can call it axioms of probability. So where there is an experiment and the sample space S and A be any event associated with it, and probability of the event is denoted by A, P of A, and this has to satisfy the following three properties. Right? So this is the axiomatic definition. So the first condition is P of A greater than or equal to 0 for every A belongs to S. That means always the probability of an event belongs to S is positive, right? P of A greater than or equal to 0, including 0 here. And second one is probability of S equal to 1, where S is the sample space. Right? That it is a property which is called as certainty property. And third axiom or third condition is if A, B are mutually exclusive events, then P of A union B equal to P of A plus P of B. So this is additive property. Suppose if this is not there, I think just for our information sake, if mutually exclusive events are not there, then we know it becomes P of A plus P of B minus P of A intersection B, right? This is the regular principle of inclusion and exclusion, right? This is the regular definition. If A, B are mutually exclusive, this becomes 0, right? Therefore, it becomes P of A union B equal to P of A plus P of B, which is additive property, what we call as. Right? That means three definitions we had. That is maybe in exams, some of the exams they may ask like write all the definitions of probabilities. One is the regular P of A equal to N by M, that is the classical probability definition. Second one is the statistical definition of probability. Third one is axiomatic definition of probability. So these three are the definitions of probabilities. Right? Now, so with this understanding, so what we do is we'll try to see some of the numericals, how to solve the problems. Right? Now there is some data collected. So in a company, there are software programmers, project managers. So and also another category is, so the type of dress they had, where they had blue dress, black or brown, and numbers, right? So like this data is given. That means actually here the total employees in the organization is 100. That is our sample space contains 100. Right? Our sample space contains 100. So out of which 80 are software programmers. Right? So out of which 20 are project managers, like this. Right? And similarly, out of 100 other ways, so with respect to color of dress, 42, 33 and 25. Right? And this, suppose if we take 35, this intersection of blue dress and software programmer. Similarly, block dress and software, this is intersections. So this is the data given. Now, if we try this problem, if an employee is selected at random, what is the probability that he is a software programmer? Right? So this is the basic question. Now, first, we recall the basic definition, right? Now, what is the sample space here? Sample space is 100, right? So 100 comes here. Right? 100. Out of this sample space 100, we are selecting software programmers. Right? Out of 100, how many are in favor of this? 80, right? So 80 are software programmers. Therefore, it is 80 by 100. This is okay. So this is the simple problem based on the basic definition of probability. So next, if an employee is selected at random, what is the probability that his dress code is of blue color? Right? So here there is no twist, no confusion. Straight away, this problem is based on the basic definition. So what is the sample space here? Sample space containing 100 employees. And how many are in favor of this event? That is blue trousers. How many are wearing blue trousers? 42, right? So therefore it is 42. So 42 by 100 is the probability related to this event. So like this, we have to use the definitions and formulas to find the probabilities required. Now we'll try one or two problems of this kind. So here we'll try to see how to solve it. In a certain residential hub, 60% of the households gets internet service from local cable company, right? And from the same company, 80% of the people will get television service. Right? So from that company, 60% are getting internet service and 80% are getting television service, and 50% are getting both internet as well as television services. Right? So this, I think this is the data given. Okay. So we need to find, or they are asking for some information like if a household is randomly selected, what is the probability that he or she get at least one of these two services from the company? That is the one question. Other question is, what is the probability that it gets exactly one of these services? Exactly one of these services. So how to do it? Okay. So here, if we see, it contains two events. One is getting internet service, getting television service. Right? This suppose if we take the internet service as A event, right? Internet service as A event. So then we had P of A, that is 60%. Right? If we take the second one as the B event, that is television service as B event, right? And this 80% is P of B, right? And 50% is nothing but getting both, that means P of A intersection B, that is both the services, right? Okay. Now, how to answer this, whatever it is. So that's why in general, to answer most of the questions related to probability, most of the times we can jump into the Venn diagram approach. Right? So most of the times Venn diagram approach helps us to solve many of the problems based on the basic probabilities. How we can say it. Next slide. Right? So now we'll take the Venn diagram, right? So this is the internet service, and this is television service, and this is both, right? So from the given data, so 50% are getting both, right? 50% are getting both. So internet as well as TV service. So 50%. Okay. Next, internet service, total 60%, right? Total 60%, out of which 50 are already in intersection, therefore 10 comes here, right? Right? I hope that it is clear, right? Now 80% are getting television service, so 50 already there, so 30, right? Okay. If you see here whether what we have done is right or wrong. So if you see here, how many are getting internet service? 60%, right? 10 plus 50. Right? So how many are getting television service? 50 plus 30, right? And how many are getting both? 50%. So once we had clarity, now just for our understanding says, what is this 10 stands for? What is this 10 stands for? Getting only internet service, only, right? And what is this 30 stands for? Getting only television service, right? Now coming to what they asked for is, what is the probability that the selected person get at least one of the services? At least one of the services. So at the beginning, I think we discussed it. At least means it is union, right? Union. So P of internet union television. So then this is the formula, P of internet plus P of union, P of television minus intersection. The regular formula, P of A plus P of P minus P of A intersection B. Right? So we know P of A 60%, P of B 80%, intersection is 50%. Therefore, we get 90%. Or otherwise, union we know, right? We need not, don't require any formula. Just if you see, union is nothing but the complete part, right? 10 plus 50 plus 30, therefore 90%. So next question is, what is the probability or percentage of the people who are getting exactly one service? Right? Exactly one service means, now already we have seen this 10% getting exactly internet service, this 30% getting exactly television service. Therefore, the percentage of the people getting exactly one service is 10 plus 30, that is 40%. Okay. Right. So that's why in probability, so every problem will have its own logic. So instead of the depending on the logic required, most of the times, so we can try to solve the problems with the help of Venn diagram approach. Okay. Yeah. Next, another example. A problem in statistics is given to three students P, Q and R, and the probability that P solves it is 1 by 2, Q solves it is 3 by 4, R solves it is 1 by 4. Right? So problem is given to three students, when the probabilities that they can solve the problem are given. So here one assumption is assuming that these solving the problem by P, Q, R are all independent. Right? So these events are independent events is the assumption. Then what is the probability that the problem is solved? Right? So how to find this? So what is the probability that the problem is solved? Right? That is, it can be solved by at least one, right? At least one. At least one, right? Either it can be A, or it can be B, or it can be C, right? So here, if you are able to understand that, then I think the problem is done. Right? So that means here we have to, one way of understanding it is nothing but finding the probability of, P union Q union R. This is what we have to find. This is what we have to find. So that means solving the problem by at least any one of these. That is either by P or Q by R, either by both combinations or by all the three. Finally, the problem is solved. So then what is the logic we can use? So here one logic is, right? So assuming that raw way of doing the problem or raw way of solving the problem, as I discussed, right? So all possibility, that is here if you see only A solving the problem, right? Only A, B and C are not able to solve the problem. Here only B can solve the problem. Here only C can solve the problem. Right? And here only A and B can solve the problem, not C. Similarly, AC solves the problem. Similarly, BC solves the problem. Right? And here A, B, C. Right? So out of all these, now this won't come, right? This is nothing but no one can solve the problem. This won't come into picture. Right? This won't come. Right? Now, so sum of all the probabilities. So P of A intersection B intersection C plus P of A intersection B bar intersection C bar and so on. Right? Then because they are independent events, we know the rule, right? P of A intersection B equal to P of A into P of B. So that can be extended for any events. Right? So that is the raw way of doing it. Right? So I think we can try it later. Right? So our smart way of doing is as discussed. So it is nothing but P of P union Q union R, right? This is right. Right? At least one of them. But here also the problem is there. P of A union B union C, we had a formula like the P of A union B, we know, right? P of A plus P of B minus P of A intersection B, right? Similarly, for three events, the formula is there, which is lengthy, and that relevant information is not available. So what is the information that we had? Only probabilities of P, Q and R. And other information is these are all independent events. Okay. So then at least one of them solving can be right. Now we know P of A can be written as 1 minus P of A complement, right? This is P of A, suppose if we take, which is nothing but 1 minus P of A complement. Right? Right? I hope that's clear. P of A equal to 1 minus P of A complement. Now, De Morgan's laws was something called as P of A union B whole bar equal to P of A bar intersection B bar, if you remember. Right? So this becomes P of P bar intersection Q bar intersection R bar. Right? Since these are independent events, we can write them separately. P into P bar plus P into Q bar plus P into R bar. Right? Right? So here what is the concept? What are the concepts we used? P of A we wrote as P of 1 minus P of A bar, right? And here we use De Morgan's law from set theory. P of A union B whole bar equal to P of A intersection P of B bar. So now we know P of P bar means complement, right? So 1 minus 1 by 2. Q means 1 minus 3 by 4. 1 minus 1 by 4. If you simplify, you will get 0.062. So this is another way of solving the problem. So that's why in probability, basic probability related problems, we can have our own logic and we can have our own way of understanding and solving the problem. So another example, a committee of 5 is to be selected from a group of 5 men and 8 women. Right? So we had that means sample space, if we take, consisting of 5 men plus 8 women, that means total 13 women. From this, the event is selecting a committee with 5 people, right? Selecting a committee with 5 people. And now what is the probability that 5-member committee selected contains 3 women and 2 men? Okay. Right. So here the sample space is 5 men and 8 women. From that they are selecting, event is selecting 5 people, and these 5 people which are going to be combination of 3 women and 2 men, right? So how to understand and how to solve this problem? Okay. So now this is, I think, in a broader sense. So sample space contains 5 men, 8 women, that means total 13. Right? And out of 5 we have to select 2 men. Out of 8 women we have to select 3 women. So that finally the committee consisting of 5. Okay. So to solve this, if you see, we use a term called as selecting, right? Out of 5 we are selecting 2. Out of 8 we are selecting 3, right? So for this we need some understanding or some concept that is nothing but combinations. Right? How many ways that we can select 2 men out of 5, right? 3 women out of 8, like, right? So that is where combinations, that is I think we are from NCR, what we call as, right? So NCR, right? So that concept is required to solve this problem. Right? So basic understanding is the same, that is we are going to use the same basic definition of probability only, But to find the numerator as well as denominator, we need to go for selection of men, women from the sample space, right? So where we have to use something called as combinations. Permutations and combination we are familiar, right? Okay. So we see how. Right? First, we, as usual, we have to see what is our denominator, right? Sample space, right? So samples space. Now random experiment is what? Selecting 5 from a group of 13, right? Right. Right. So total what we had is 15 people. 5 plus 8, that is 13 people. Out of which we have to select 5. Right. So that means how many ways we can select this, right? So that is 13C. Out of 13, we are going to select 5 people, right? So 13C5. Right? So these are the entries that we are going to have in the sample space, right? Clear? I hope that is clear, right? So out of 13, we are selecting 5, so which can be done in 13C5 ways. And the formula for NCR is n factorial by n minus r factorial into r factorial. That means here 13 factorial, 13 minus 5 factorial into 5 factorial. Then if we simplify, so now our sample space contains 1, 2, 8, 7. So this is the denominator. Now coming to numerator, that is event A, which is nothing but selecting 3 women out of 8, right? And 2 men out of 5 men, right? So selecting 3 out of 8, which can be done in 8C3 ways, and selecting 5 men, selecting 2 men out of 5 can be done in 5C2 ways. Now same formula, 8C3 means 8 factorial by 8 minus 3 factorial into 3 factorial. Similarly 5C2, so 5 factorial by 5 minus 2 factorial into r factorial. Here the formula is NCR equal to n factorial by n minus r factorial into r factorial, right? So 560 are in favor of this event. So 1287 is the total in sample space, out of which 560 are in favor of this. So therefore the probability is this. So this is so sometimes we require this way of understanding where selecting balls, selecting committees kind of scenarios. So where we have to use the concept combinations. Okay. Now another interesting example is what is the probability that a leap year selected at random will contain 53 Sundays? Right? Probability that a leap year selected contains 53 Sundays. And next is a non-leap year selected contains 53 Sundays. And another example is a year selected. We don't know whether it is a leap year or non-leap year. Then what is the probability that it contains 53 Sundays? Okay. 3 problems here. So one is leap year selected, then what is the probability that it will contain 53 Sundays? Other one is selecting a non-leap year, and what is the probability that it will have 53 Sundays? And other problem is selecting a year, then what is the probability that it will have 53 Sundays? Right? How to do this? So very simple. So in general we will have 52 weeks, whether it is leap or non-leap year. In general, so you will have 52 weeks. That means you will have 52 Sundays, 52 Mondays, 52 Tuesdays, Wednesdays, like this. Right? So after 52 weeks, if it is a leap year, then 2 days left, right? If it is a leap year, you will have 2 days left. If it is a non-leap year, you will have 1 day left. Right? So if it is here in this case, it is a leap year selected, right? So already 52 full weeks are there. That means 52 Sundays already available. Right? So left over are 2 extra days, right? The 2 extra days can be any combination because it depends on what day the year started, right? So therefore, the 2 extra days can be combinations like Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, Friday, Friday, Saturday, Saturday, Sunday, like this, right? So total 7 combinations, right? So 7 possibilities where we can have 2 extra days, right? Now, out of which, how many are in favor of getting a Sundays? Extra Sunday, that is, when we get 2 combinations, that is Saturday and Sunday, out of the 7 combinations, Saturday and Sunday, that means we had extra Sunday. And other combination is Sunday, Monday, right? Sunday, Monday combination gives one more extra Sunday, right? That means out of all these 7 combinations, 2 combinations are in favor of getting extra Sundays. Therefore, it is 2 by 7, right? Okay. Leap year. Now, same if we continue, in case of non-leap year, what happens? I think once this is clear, very simple. So non-leap year means only one day left. That one day can be any day, Monday, Tuesday, Wednesday, and so on up to Sunday. That means 7. So what is the favorable case here? That means what is the favorable case to have extra Sunday? Only one possibility, that is Sunday, right? Whenever Sunday comes, that is in favor of this event. So therefore it is 1 by 7. Right? Clear? Now going to the next one. Year selected. Right? So here we don't know whether it is a leap year or non-leap year. So leap year you will have extra Sunday, 53 Sundays. Non-leap year also you will have Sundays. So that means here previous case we already selected the year. We selected already leap year. Then we know the probabilities. And we know already non-leap year. But here first we are selecting year. Right? Okay. So that year can be leap year or it can be non-leap year, right? So what is the probability that a year selected is a leap year? So leap year will have for every once in 4 years, right? Therefore it is 1 by 4. Right? So non-leap year 3 by 4, right? So now if it is a leap year, just now what we discussed, what is the probability of having extra Sundays? That is 2 by 7, right? And non-leap year already we discussed earlier, that is 1 by 7. Now if you use the multiplication law of probability here, 1 by 4 into 2 by 7 is related to getting 53 Sundays, right? If it is a leap year. And 3 by 4 into 1 by 7 is related to getting 53 Sundays in case of in case if it is a non-leap year, right? Now total, these two are mutually exclusive, right? Therefore we have to sum these two. Therefore it is 5 by 8. Clear? So that is the difference. They are already year selected. So therefore straight away we jump into the regular formula. Here we have 2 ways, 2 steps. One is year selected. It has to be a leap year or it can be a non-leap year. Then comes extra Sundays. Yeah. Get right. Now another example to understand the basic stuff only. A speaks truth in 80% cases. That means 0.8 is the probability that A speaks truth. And B speaks truth in 60% of the cases. Right? So or the probability that B speaks truth is 60 by 100. They here 80 by. Now what percentage of cases are they likely to contradict each other in stating the same fact? Right? So what are the possibilities that each one A and B contradict each other? Right? So how to find and what is that we have to find here? Okay. So very simple here, just if, here that's why in probability understanding the given data is very crucial and very important. Right? So what are the possible cases happens? One is A speaks truth, right? A speaks truth where B contradicts, right? Here A is stating the truth, B is contradicting it. Other one is B is speaking truth and A is contradicting here, right? Okay. So here A is speaking truth and B is contradicting. Here B is speaking truth and A is contradicting. And these two are mutually exclusive, right? These two are obviously mutually exclusive. There we can use the sum, right? Now I think if you say this solving, so P of A 80%, P of A complement 20%, P of B 60%, P of B complement the 1 minus 60 by 100, that is 40 by 100. So contradicting each other means A intersection B bar or A bar intersection B. So why we are adding these two? So in mind we have to remember these two are mutually exclusive events. Therefore total probabilities P of A intersection B bar plus P of A bar intersection B. And here, so it is understood from the given data these two are mutually independent events. If they are independent events, we know the property, that is P of A intersection B equal to P of A into P of B, right? So here P of A intersection B bar is P of A into P of B bar. Here P of A bar into P of B. And we had all the probabilities required, right? P of A is 80 by 100. P of B complement is 40 by 100. P of A complement is 20 by 100. P of B is 60 by 100. So that is 44% or 0.44 is the probability corresponding. So like this we can try various problems based on our understanding of the basic probability, and few properties or rules like mutually exclusive, what happens, if they are independent events, what happens. Next, another important concept, and most of the times it appears in examination, various examinations where they'll ask us to prove this. If sometimes they'll ask us to prove this, or sometimes they will ask us to give some examples which validates these statements, right? So give some examples which validates this, that is if A, B are independent events, then A complement and B are independent. Then other one is A and B complement are independent, and other one is A complement as well as B complement are also independent. Right? So these are the three. And we know, right? So independent means immediately we have to remember that, right? P of A intersection B equal to P of A into P of B, right? Okay. That means next step we see. So this is given A, P are independent events means P of A intersection B equal to P of A into P of B. Okay. Next, so we have to prove this, right? When we can say same lines, right? If we are able to prove P of A bar intersection B, that is intersection of both these events, P of A bar intersection B equal to, that is joint probabilities, equal to product of separate probabilities, P of A bar into P of B. Okay. If this condition is satisfied, then we say A bar and B bar, A bar and B are independent events. Similarly, when we can say A and B complement are independent, very simple, joint equal to product of separate. P of A intersection B bar equal to P of A into P of B bar. Right? Then this. Similarly, A bar and B bar. So P of A bar intersection B bar equal to P of A bar into P of. So if we prove this, then we can conclude the respective statements given. So how to prove? So there are many ways to prove. So one approach is, so with the help, very many ways are there. So one approach where we'll take the help of Venn diagram. So first one we'll take, that is P of A bar intersection B will take. P of A bar intersection B will take. Now, so this we know, right? So S is the sample space, otherwise it is our universal set in set theory, where A and B are two events. Right? This we know, right? Now, A bar is nothing but, we know the basic definition also, right? A bar is nothing but S minus A, right? From from the total sample space, if you take out A, that is nothing but A bar, right? That is general set theory. Mu minus A is A complement, right? It's the same here. Okay. Now this can be written as S intersection B minus A intersection B, right? S intersection B minus A intersection B. Now same. Now S intersection B is what? Now S is the complete sample space, right? S is the complete sample space and B is this. Right? So intersection of these two are nothing but B only, right? So minus P of A intersection B. Okay. Now we know P of A intersection B is nothing but P of A into P of B, because A, B are independent events, right? Now we'll take P of B common from this. If you take P of B out, then 1 minus P of A. 1 minus P of A we know is nothing but P of A bar. Okay. So that is P of A bar intersection B, B is equal to P of A bar into P of B. That means joint of these two events is product of separate probabilities. So that is actually basic. Joint of probability of joint events equal to product of separate probabilities. Then they are called as independent events. Right? So here, so based on that we say A bar and B bar are A bar and B are independent events. Right. Now second one, I think same follows. So where A intersection B bar, right? So A intersection B bar. So A intersection B can be written as similar to the earlier discussion. B is nothing but mu minus P, that is S minus P, right? Here it is S minus P. Now this can be written as A intersection S, that means S intersection A minus A intersection B. Right? A intersection S, that are S intersection A minus A intersection B. Now similar to the previous observation, S intersection A. So S is the complete sample space, A is this. Intersection of S and A is nothing but A only. Right? Minus A intersection B. This can be separated as P of A minus P of A intersection B. Right? P of A minus P of A intersection B is nothing but P of A into P of B. Now we can take P of A common, right? Or we can take P of A out. Then 1 minus P of B. So 1 minus P of B we know is nothing but P of B complement. Right? Now same thing, right? So joint of probability of joint of these two events is equal to product of probabilities of separate events, P of A into P of B. Therefore these two events are independent events. Right? So next third one, so both combinations A bar as well as B bar, right? A bar now joint of probability of joint of these two events, A bar intersection B bar, right? And A bar is nothing but S minus A and B bar is nothing but S minus B. Generally in set theory we say mu minus A. Here mu universal set is nothing but sample space here, right? Now like previous one we separate it. So all four combinations will get S intersection S, S intersection A, and A intersection S, S intersection B, and finally minus minus plus, then we'll have A intersection B. Right? Just separate it here. S and S, right? S and S, S with B, A with S, and A with B. A with B minus minus is there, therefore we'll get plus. Okay. Now S intersection S is nothing but S only, right? And as seen previously also, S intersection A is nothing but A only, and S intersection B is nothing but B only, right? Okay. Plus A intersection B as it is. Now this can be written as, we can separate this, right? P of S minus P of A minus P of B, right? And next is P of A intersection B. Right? Next, P of S. So if we recall the axiom, probability of sample space, P of S is 1 minus P of A minus P of B. Here A, B are independent events, right? If A, B are independent events, we write P of A into P of B, right? Okay. Now, just what we do is we'll factorize this, right? Factorize this, that is factorization means here we can take P of B common here, minus P of B. If we take, then the inside we'll get 1 minus P of A. 1 minus P of A, if we take out, then it is 1 minus P of B into 1 minus P of A. So we know 1 minus P of B is nothing but P of B bar. 1 minus P of A is nothing but, this is, I think, it is a small mistake. This is A only, no complement is not there. Okay. So here again the same, probability of joint of two events is product of separate. Therefore, these two are independent events. So this is one question regularly appears for many of the examinations where probability is a part of the syllabus. So as discussed, it can be direct proof or it can be validate these statements with some examples. I think now what we do is so we'll as the time is 8:30, I think we'll stop today's session. We'll stop today's session as this is the first time that the live session is tried. So based on the feedback and suggestions related to the quality of the content and delivery of how we delivered, so we'll plan for next session. Thank you. So here we are stopping today's session. Thank you.